And then for high-speed positioning, you're also seeing the development of a lot of different non-Cartesian, or what are called parallel kinematic machines. So these are, and many of you, if you've been to IMTS and so on, you've seen machines like this. They're very interesting to watch. Machines like the Ingersoll hexapod and the Giddings and Lewis machine. And then also a lot of new other machines that have been developed in this area. Interesting new concepts where you have a lever principle over here, so what are called parallel kinematics. So there's a lot of these that are coming out, and these are also mainly for high-speed positioning type of applications. So they're not yet in practical use, but they are finding some applications, and you see more and more of them in the market. The real issues still with these type of machines are the accuracy and repeatability. You're still talking about accuracies of plus minus 1,000s, plus minus 2,000s on these machines. There are issues with controlling thermal effects. The programming is quite complex. For example, on a machine like this, if you had to move in a straight line, you can see that you have to program a lot of axes just to move in a straight line. And relatively a large physical size for a very small working envelope. So if you look at these machines, they're quite huge. And when you look at the work pieces that are machined, they're normally like this. So you have a huge machine structure for relatively a small working envelope. And what we are finding, we've done some experiments at Mikron with these type of machines. They're not suitable or practical for complex 3D contouring applications. So when you talk about the diamole field, let's say if you had to machine a surface to within 10 microns or 4/10 or so, there is a lot of difficulty in these type of machines to get those accuracies and to get the surface finishes.